Before considering more details regarding the closed-loop control systems, we want to have a quick look at the behavior of the open-loop control systems. This is just to show you why closed-loop control systems would be more desirable for us. So initially we discuss about the steady-state behavior or analysis of open-loop control systems. You just need to keep in mind that in the case of open-loop control systems, we will have a controller, GC, and a plant, GP, with some disturbance added to the output of the plant in this. Okay, and then we will get the actual output. COS we can call it, R as the input. So you can see that here we don't have any feedback. The output is not measured. So this is not, let's say, something that we have. The output is not measured. It is not being compared with the reference. So the overall structure is much simpler than the closed loop control system. And as a result, the overall system will be cheaper as well. We can construct the open loop control system much cheaper than the closed loop ones. However, as we will see in this lecture, the open loop control systems are not showing us the desired behavior that we want from the control system. So to begin with, we will consider the case of a DC motor. We already know that the transfer function for the DC motor in terms of its speed as the output variable is given in this form. So we have GP of S given as K over R plus SL times B plus SJ plus K squared. If you want to obtain the steady state value of the output, which is the speed, given the steady state value of the input voltage, which is considered as USS, you will get this. So CSS will be in the form of GP evaluated at 0 times USS. I hope this is clear for you, but just to give you an idea, when you want to obtain the CSS, the steady state value of the output, it's indeed equal to limit of S times C of S as S goes towards 0. You should know this already. And CS is equal to GP times U. U is the input. GP is the transfer function for the process. Indeed, you should also know that GP is equal to C, which is the output, over U, which is the input. Therefore, C is equal to GP times U. So it should be something clear. And here we also have assumed that the steady state value for U is USS, as you can see here, U of S, and therefore CSS will be equal to, you can write it in this form, limit of S US as S goes towards 0 times limit of GP S as S goes towards 0, and therefore we will get USS times GP evaluated at 0. And if you replace S with 0 in the transfer function that we have for GP, you will get CSS equal to K over R B plus K squared times USS. And that's what we have over here. So the steady state value for the speed of the motor will be, let's say, proportional to the steady state value that we have for the input voltage. On the other hand, the input voltage for the DC motor comes from the output of the controller, as you can see over here. We have the open loop controller here, which gives the input voltage determines the input voltage for the DC motor, and therefore since we are the one who is going to design the controller, now we have the opportunity to design it in a way that CSS, the actual steady state speed of the motor, is equal to the reference value that we have received. Here we have the reference value. And that means that we should make the overall transfer function in the steady state mode over here being equal to 1. If we replace USS with with the actual signal that comes from the reference multiplied by the transfer function that we have for the open loop controller, and if for the open loop controller we assume that the DC gain of the controller is equal to K, then we can rewrite the equation in this form. CSS will be equal to K over RB plus K squared times, now instead of USS we can write down K, which is capital K, which is for the DC gain of the controller, times R bar, and R bar is the constant reference that we have received. And we want this to be equal to R bar indeed. Therefore, this part should be equal to 1. In other words, K should be equal to RB plus K squared over K. This is capital and the others are lowercase. So if we have this case, if we set the DC gain of the controller to RB plus K squared over K, which is indeed equal to 1 over GP evaluated at 0, or the DC gain of the plant, then in this way we don't need the sensor in it to measure the output, and there will be no sensor noises. Of course, the overall design will be much cheaper than the feedback control system. So it seems that it is in some sense it's a good choice, yeah. But why don't we just continue with the open loop controllers, and why do we choose to use the closed loop controllers? There are a couple of reasons. The first one that we are going to consider is regarding the stability. So our plant, the actuator plus process that we have here, GP of S, might not be stable at the beginning. Okay, so or it might be an unstable plant by its own. And when we want to have the control system, we want to have the overall system being stable. And here we can see that by the introduction of the open loop controllers, we cannot stabilize our overall system. And that's because we cannot indeed move the poles of the transfer function for the whole system by introducing an open loop controller. While, as we will see later, this is possible by introducing the closed loop controllers to our system. Okay, so over here you can see that C of S is obtained as GC open loop times GP times R plus D, which is the disturbance term. Or we have L of S times R plus D of S. And L of S is called the loop transfer function. If we want to have the open loop stability, the poles of both GCOL and GP should be on the left-hand side of the S plane, which is indeed this area. If this is the S plane, all the poles should be on the left half plane. So if GP originally has pause on the other side, on the right side, anywhere here, let's say over here, by no means we can make the overall system being stable by the introduction of the open loop controller, of course. And you shouldn't also think about canceling unstable pause of GP. Okay, it's not a proper approach indeed. The overall system will not be BIBO stable. So you can see that stability is one main fact for designing the controllers and for our overall control system. And by the open loop controllers, we might not be able to have a stable system.